Okay, welcome everybody to our second lab test review podcast for the term. This is going to go over uh, the lab that we had revolving around the anatomy of the heart and how to interpret an EKG. Remember, again, not to use these video podcasts or these presentations as a substitute for coming to lab or going to biosis. This is simply meant to uh, improve your performance on the upcoming lab practical. So let's start with identifying the indicated chambers on each of the following slides. Okay, so we're looking here at the front of the heart. We can tell this because we can see the pulmonary trunk coming right off the front. Okay, so we know that this is going to be the right side of the heart, and this is going to be the left side of the heart, and the chambers are as indicated. Okay, the reason that the upper chambers are termed auricles in this picture is because these loose flaps of tissue look a little bit like ears. They fill with blood as it returns in the right auricle from the body and in the left auricle from the lungs. What eventually happens, of course, is that the auricles will squeeze and force the blood down into the lower chambers, which are the ventricles, which, as you can see, are a lot more muscular. You can see here the interventricular sulcus, indicating the dividing line between the left and the right ventricle in this model. Next picture we want to look at is the back of the heart, and we want to indicate the relevant chambers. So remember, we're looking at it from back to front. The chambers are indicated as follows. You can see the left atrium receiving blood from the right and the left pulmonary veins. You can see the right atrium, which receives blood from the superior and inferior vena cava. Down here, you can pick up the posterior aspect of the left ventricle. This is a little bit more unusual diagram. This is the front of the heart removed, and you're looking again back to front. But again, to orient yourself, you have to look for the thickened walls of the left ventricle in order to understand which chamber is which. If you do that, you can see the left ventricle is located here. As a result, the chambers are as follows. Okay, notice that you can see the papillary muscles in the chordae tendineae in the lower portions of the ventricle down towards the apex, and you can see the auricles, the upper chambers, of course, above them. This is the heart from the Brown torso model. We're looking again at the front. How can we tell? Well, we can pick up the pulmonary trunk, the aorta, okay? My mistake here, the pulmonary trunk and the aorta here. This is the superior vena cava, and this, of course, is going to be the right side of the heart. This is the left side. The chambers are as follows, okay? So make sure and know what the heart looks like from the outside. This is the same model seen from the back. There's a lot of subcutaneous fat in this model that's attached to the heart muscle itself. That's one of the reasons why the rear view of this model looks a little different than the other heart model from the pink torso. But again, the chambers are as follows. Okay, this is the left side of the heart. This is the right side. You're looking from back to front. From back to front. Okay. Relevant vessels. Okay, that you can pick up. These are the pulmonary arteries. These are the pulmonary veins, and you can see here the inferior and superior vena cava. Okay, you can pick up just the tiniest bit of aorta over here, and this is, of course, the coronary sinus. Okay, this is the heart from the Brown torso opened, looking at it from the inside out. This would be the front half of the heart. The front of the heart is actually resting on the table surface. This would be the back of the heart. It's actually resting on the table surface. And again, to orient yourself, you have to look for the thickened wall. And you can see here the thickened wall of the left ventricle. The other major clue, of course, is that you can pick up now um, the aorta. Okay, so you can pick up the left ventricle here, the aorta leading into it. The exit, of course, from the left ventricle is the aorta. The exit from the right ventricle is the pulmonary trunk. Okay, so if we put this heart back together, right, so that we're looking at it, you can imagine you slap this over the front, okay, and you would get a picture very similar to this one, all right. You would see the following chambers, okay, right atrium and ventricle, left atrium and ventricle. Again, you look for the thickened wall as the indicator of which is the left ventricle. Okay, so you can see here we have a thicker wall in this region. Also, the other major clue, of course, is that the aorta comes straight off of the left ventricle. Okay, the following structures in these pictures we want to identify. The apex would be here, right? The auricles here, the base of the heart, the widened portion that's above the apex, the interventricular septum. You can see here, it's the wall between the two ventricles. It's indicated with the heart reassembled by the interventricular sulcus. Okay? Remember, right side of the heart, left side of the heart. Okay? The atria are the upper chambers of the heart. They have the flap-like tissues that surround the atria on the outside. They expand when they fill with blood. Next, we want to do some valve questions and identify the valves on the following slides. Again, we're looking at the heart from front to back, all right? So this would be the left side, this would be the right side, and the valves would be as follows. You can see pulmonary semilunar, bicuspid, and tricuspid. The valve you cannot see is the aortic semilunar because it is underneath the IV septum, not visible in this diagram. Okay. The valve IDs on the brown heart, butterflied open for you to see, are as follows. Okay. You can pick up the pulmonary and aortic semilunar, the tricuspid, and the bicuspid. Okay. Notice where they all come out. Notice the pulmonary semilunar is at the base of the pulmonary trunk, the aortic semilunar at the base of the aorta. Okay, what valve is found at the base of this vessel here? This is the aorta. The aortic semilunar valve would be at the base. What valve is found at the base of this vessel? And it would be the pulmonary semilunar. The pulmonary semilunar. ID the two indicated structures and they're associated with what valve function. These are the chordae tendineae and the papillary muscles. The purpose of the chordae tendineae is to ensure that the atrioventricular valves only open in to the ventricles. They also help to pull open the atrioventricular valves when the pressure in the atria is greater than the pressure in the ventricles. This is the atrioventricular valve known as the bicuspid. This, of course, is the tricuspid. Okay, give another name for the left AV valve, and that would be the mitral or bicuspid valve. Give another name for the right AV valve, that would be the tricuspid. Give another name for the mitral valve, that would be the bicuspid. Name the two valves that have chordae tendineae attached to their flaps, and those are the tricuspid and bicuspid. How many cusps are found on each semilunar valve? That would be the aortic and the pulmonary, and the answer is 3. Which valves prevent the backflow of blood into the right ventricle? And the answer there is the pulmonary semilunar. And which valves prevent the backflow of blood into the left ventricle? And that would be the aortic semilunar. Okay, identify the indicated vessels on the following slides. Here again, we're looking at the front of the heart. Okay, so this is the right side, this is the left side. So the vessels are as follows. Okay, you can see the superior vena cava, the inferior is hidden from view, pulmonary trunk, aorta, left pulmonary vein. Right pulmonary vein would be over here somewhere, but you can't really see it that well. And here we're looking at the back on identify the following vessels. They are as follows. Okay, you can see the descending aorta, superior and inferior vena cava, pulmonary veins, and down here, of course, the coronary sinus. The job of the coronary sinus, remember, is to return blood from the heart muscle itself to the right atrium. That, along with the blood return from the superior and inferior vena cava, is what dumps blood into the right atrium. Okay, identify the following structures. They are as follows. Superior vena cava, you can see here, pulmonary trunk, aortic arch, which is the gateway to the body for oxygenated blood, left pulmonary veins. The right pulmonary veins you can't see because they're behind the heart model. Here, they return oxygenated blood to the left atrium from the lungs. Okay, the heart from the brown torso model. Name the following vessels. Okay, so they're as follows. Superior vena cava, you can see here, aorta, pulmonary trunk, pulmonary vein, and then down here we have some circulation to the heart muscle itself. You can see the right and the left coronary artery. They branch off of the base of the aorta. Okay, very important to know that. The heart muscle requires a lot of blood. It has a lot of work to do. As a result, it gets first dibs on the blood that it actually pumps to the body. This is the same heart model from the back. The vessels are as follows. Okay, you see the aorta, the pulmonary trunk, which is going to lead to the lungs, the left pulmonary and right pulmonary veins, superior and inferior vena cava, and of course the coronary sinus. Now, something I want you to take special note of is the fact that in the pulmonary circulation, the veins are red and the arteries are blue. And the reason for that is that the arteries in the pulmonary system are carrying deoxygenated blood that is returned from the body back to the lungs, while the veins are returning oxygenated blood from the lungs back to the heart. Okay, so very important to keep that in mind. A lot of people get confused because they always think that veins are blue and arteries are red. And what you want to understand is that what distinguishes an artery from a vein is the direction relative to the heart. Arteries always carry blood away from the heart. Veins always carry blood back towards the heart. Here we can see the brown heart butterflied open. This would be the back of the heart. This would be the front. Okay, we've bisected it. The vessels are as follows. Okay, you can pick up the pulmonary trunk and the aorta as seen here. These two indicated vessels come from the ascending aorta. You see these little openings down here? This is the back of the heart. Okay, this would be the right side. This would be the left side. Okay, and what you're looking at here is the right and the left coronary arteries. Okay, so be very careful. All right, make sure and understand that this is the blood supply to the heart muscle itself. Okay, all right, moving on to the sheep heart dissection. Okay, now we want to look at the sheep heart that you worked on in lab, and what we have here is a look at the front of the sheep heart. So we can tell again that this is the right side of the heart, this is the left side of the heart, and the way that we can tell that this is the anterior is we look for the anterior interventricular sulcus, okay, and the interventricular artery runs right down this little groove here. The The other way that you can tell is if you look up towards the top, you can see a little bit of pulmonary trunk, and that always comes off the front of the heart. Okay, so this is the anterior surface. Next question we want to answer: what are the indicated pointers A and B located in? And they are located A in the pulmonary trunk and B in the aorta. The aorta is always going to be posterior to the pulmonary trunk. Okay, comes right out behind it. And remember, we stuck our fingers in each of those vessels, and we were able to enter the right ventricle in the case of the pulmonary trunk by going through the pulmonary semilunar valve, and we were able to enter the left ventricle through the aorta by going through the aortic semilunar valve. The vessels shown here on the back of the heart are the superior and inferior vena cava. Okay, superior vena cava drains into the right atrium, bringing blood from the head, the neck, the shoulders, and areas above the heart. The inferior vena cava brings blood from areas below the heart into the right atrium. It's a little tough to see on your dissected hearts. It runs at a right angle to the aorta and the pulmonary trunk. Remember that the heart tilts with the apex pointed to the left in your chest, and essentially the superior and inferior vena cava run parallel to the aorta. All right, after the aorta comes down behind the heart, those two vessels run right alongside each other. So one of the things that you can do when you cut the aorta, remember that the aorta forms a big arch that loops around to the back of the heart, and our hearts are cut so that the aortic arch is actually missing. But this forms essentially almost a cross when you put the probe into the vena cava and also into the pulmonary trunk and aorta as they come straight out of their respective chambers. Okay, so they run at right angles to each other. What valve would be located inside the heart in the area penetrated by pin A? Well, we're penetrating the pulmonary trunk, so we would penetrate the pulmonary semilunar valve there. Here we have a heart that's been opened up, and it's very easy to see the left ventricle here and the right ventricle over here. Look how thick the walls are in the left ventricle. Okay, so this is the left side of the heart, and they're asking now which valve is which, and what we see is that A is stuck in the tricuspid, which is the doorway between the right atrium and the right ventricle, and B is stuck in the bicuspid, which is the doorway between the left atrium and the left ventricle. Identify the following structures. Again, this is a heart that's been sectioned coronally. A is indicating the papillary muscles which attach to the chordae tendineae, indicated by B. C is the bicuspid valve, and D, the aortic semilunar valve, which is the doorway out of the left ventricle. Okay, know what those structures look like. Okay, this is another sagittally sectioned heart. They're asking you which valve is indicated by A. That is the aortic semilunar valve. Okay, remember that it leads into the left ventricle, and the interventricular septum is the area indicated by B. Remember that the aortic semilunar valve only opens going out of the heart, whereas the atrioventricular valves only open going into the heart. Okay, keep that in your head. Next question, identify this vessel, and what organ does blood first encounter after passing through it? Okay, well, this vessel is the pulmonary trunk, and the valve is the pulmonary semilunar valve, and the organ that blood encounters after passing through this vessel is the lungs. Okay, how can we tell? We can tell because this is indicating the right ventricle. Remember, the doorway out of the right ventricle is the pulmonary trunk. The pulmonary trunk. This is just a diagram showing you the path of blood through the body systemically. We ask the following questions. Number 1 in the upper right, is this vessel an artery or a vein? It is a vein. How do you know? It is carrying blood back to the heart. Question number 2, are these capillaries in the pulmonary or systemic circuit? They are in the systemic circuit. They are delivering oxygenated blood to the body. Next question, is the blood in this vessel oxygen rich or oxygen poor? It is oxygen poor, as evidenced by the blue color of the vessel, which indicates that the hemoglobin is not fully saturated with oxygen. Next question, the cardiac output is passing through vessel 1 is what compared to that passing through vessel 2? And the answer is equal to. It is always equal to. Let's circle that for emphasis. Okay, and the reason for this is that if the two sides of the heart did not deliver equal volumes of blood with each stroke, what would happen is that fluid would build up in either the systemic or the pulmonary circuits. Okay, so if we look here, we want to circle right here, equal to. If the right side of the heart slows down, what will happen is that blood will not be pumped to the lungs as fast as it's returning from the body, and this will result in peripheral edema. And that would be right side failure, or slowing if you wish. The left side of the heart slows down, you're going to have pulmonary perfusion. This is basically liquid in the lungs. And the reason for that is that the left side of the heart can't keep up with the right side. What happens is that blood is going to tend to pool in the lungs. The result is that the lungs are going to slowly fill with fluid. Okay, next question. The blood pressure in vessel 1 is what compared to that in vessel 2? And the answer is less than. Okay. Now, why is this the case? Why is it less than? Well, the reason that it's less than is because of the distance between the heart and the lungs compared to the heart and the body. The lungs and the heart are very close to each other. As a result, the pressures are very low in the pulmonary circuit. They're much higher in the systemic circuit because the heart has to work against greater resistance. Next question. For each of the numbered vessels below, state what valve would blood pass through when it next encounters its path through the body. Okay, so let's start with vessel number 1, the coronary sinus on the back side of the heart. What's that going to drain into? That's going to drain into the right atrium. The right atrium is going to pump the blood into the right ventricle through the tricuspid valve. The tricuspid valve. Okay, we'll indicate these as we hit them. Let's do this in yellow. Okay, so we will write here tricuspid. Okay. Question number 2, what valve are we going to see next? Well, these are the pulmonary veins. The pulmonary veins drain into the left atrium, so the next valve you're going to see is the bicuspid. Okay, next question. Question number 3. What vessel is this? Well, this is the superior vena cava. Superior vena cava drains into the right atrium, so the next vessel we're going to see is the bicuspid. Number 4, pulmonary trunk. Pulmonary trunk brings blood to the lungs, where it gets oxygenated, returns to the lungs through the pulmonary veins. The pulmonary veins drain into the left atrium. The next valve we're going to see is the bicuspid. Number 5, aorta. Aorta sends blood to the body, where the oxygen and nutrients then get used by the body's cells. It then returns to the heart through the superior and inferior vena cava, and as a result, the next valve it's going to see as it passes from the right atrium into the right ventricle is the bicuspid again. Down here, number 8, okay, is the anterior interventricular artery. It is going to send blood to the heart muscle. That blood will then be exhausted of its oxygen and its nutrients by the heart muscle and then will return to the heart chambers via the coronary sinus on the back of the heart, which drains into the right atrium. As a result, the next valve that that blood is going to see is the tricuspid valve. Okay? You have to be able to do those exercises. Those are the kinds of questions that you'll likely see on the practical. Next question. Starting with the blood leaving the chamber indicated by the black arrow, give the sequence that blood would pass through the 5 labeled structures on its way in returning to the starting chamber. Your answer should be a sequence of 5 letters, and the proper sequence, we'll indicate here in blue, is AECBD. And if you want to verify that, we start here with this arrow, the left atrium, okay, draining into the left ventricle, from there to the aorta. Aorta sends blood to the body. Returns where? Through the superior and inferior vena cava, okay, which you can see here. There's the superior vena cava, inferior's down here, all right. Next thing we're going to do after we enter the right atrium, we're going to go to the right ventricle. The right ventricle will then pump the blood to the pulmonary trunk, okay, and so the right ventricle is here, C, the pulmonary trunk here is B, and then the pulmonary trunk leads to the lungs, blood will become oxygenated, will return to the heart through the pulmonary veins, which drain into the left atrium, D being the last on our trip. Okay? All right, true or false? All of the indicated red vessels either enter or leave the left side of the heart, and the answer to that is absolutely true. Okay? And second question, all of the indicated blue vessels either enter or leave the right side of the heart, and that is also true. Okay, and if you review the path of blood through the heart, you'll see that that's the case. Next question, after blood passes through valve A, what would be the next valve it would pass through on returning to the heart? Okay, it would be the tricuspid valve, Whoops, back up. Okay, and we have to think about that, right? Because what's happening here? The blood is passing through valve A, all right, and valve A is essentially leading out, of the left ventricle. What will happen next is it will head out to the body where oxygen will be used up. It'll end up back at the heart in the right atrium. Right atrium is going to pump the blood through the tricuspid valve into the right ventricle. Okay, next question. Does oxygen and carbon dioxide content of the blood change from the time it passes into the heart through the pulmonary veins and out of the heart through the aorta? And the answer is no. Does the oxygen and carbon dioxide content of the blood change significantly from the time it passes into the heart through the superior inferior vena cava and out of the heart through the pulmonary trunk? That answer is also no. Okay. While the blood is in the heart chambers, the oxygen content does not change. Okay. The heart muscle, the organ, gets its oxygen from the coronary circulation, and that begins once the blood enters the aorta. Okay. From what structures does the coronary sinus return blood to the right atrium? And the answer is the heart muscle. Okay. All right. Next thing I want to do is talk a little bit about EKG and cardiac output. And what we have to understand about EKG is that it's a method of reading electrical activity in the heart, and it's a series of electrical and mechanical events that always occur in the same sequence. Remember that the three parts of an EKG are the P wave, the QRS complex, and the T wave. Okay? And if we were to draw this, let's draw this just big for you to see. You can see little versions of the wave here. I'm just going to draw a big version of the wave. So this would be the P wave, then the QRS complex, and the T wave. Okay? P, QRS, and T. Now, what do each of these represent? Okay, the P wave here represents atrial depolarization. And it's followed by what? Leads to atrial systole. Okay, so depolarized, then the atrial squeeze. That systole happens right around here, atrial systole. The QRS complex represents two events, right? Represents atrial repolarization and also ventricular depolarization. All right, and that's followed by what? That's followed by ventricular systole, which happens right about here. Okay? And the T wave, the last of the bumps, is ventricular repolarization. And that is followed by ventricular diastole, which happens right about here. What can we use the EKG for? Well, we can use it to ensure that the conducting system of the heart is working the way that it's supposed to. We can also use it to determine the heart rate. Okay? So let's take this first question, a heart rate question. A 6-second interval of time is indicated on the EKG seen above. The average heart rate during this interval was what? How many beats per minute? Okay, well, we got to count here. Let's count the number of beats. Okay, I see 1, 2, 3, 4, 5, 6. What we can do is we can basically tick these off. 1, 2, 3, 4, 5, 6 beats within the interval. Okay, so what we've got there is 6 beats in 6 seconds. And what we want to know is how many beats per minute that is. Well, we got to do our conversions here. So we know that there's 60 seconds in a minute. And so if we do our units cancellation, the seconds go away. We're left with beats per minute. Okay, so that's going to be 6 times 60 beats. Okay, divided by 6. So that works out like this: 6 times 60 over 6, and that's going to be in beats per minute, because that's the only unit left after we do the cancellation. The 6's will cancel, and we're left with 60 beats per minute. Okay, so that's how you do that. Basically, you count the beats that are within the interval. Okay, within the interval. So the number of clicks within the interval, that's the number of beats in that amount of time. Okay, don't count them if they're on the line. Another one, 10-second interval of time in the indicated EKG. How many beats per minute? Well, let's count them again. So if we count, what do we end up with? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we got 10 beats in 10 seconds. Okay, 10 beats in 10 seconds times 60 seconds in 1 minute, okay, is going to do what? Seconds will cancel, all right, and we'll end up with 10 times 60 over 10, and that's going to be in BPM, beats per minute, okay, and what will happen is that the 10s will cancel, and we'll get 60 beats per minute. Okay, that's how that works. How about this one? A 3-second interval. How many beats per minute? It's the same idea. Okay, count the beats. So we have what? We have 1, 2, 3 beats. 3 beats in 3 seconds. Multiply that by 60 seconds in 1 minute. What do we end up with? Well, the seconds cancel. We end up with 3 times 60 over 3 BPM. The 3's cancel. 60 beats per minute. Okay? Not too bad. All right. This is just a or a recanting of what I just showed you in the first diagram. What do the different parts of the EKG indicate? The T wave is correlated with ventricular repolarization, the P wave with atrial depolarization, and the QRS wave with ventricular depolarization. Okay, so let's fill those in. Ventricular, and this one is atrial, and this one down here is ventricular. What are the different waves here? There's the P wave, there's the QRS, and it of course is our T wave. Okay, our T wave. Good. Identify each of the EKG waves shown below. Well, that's not too bad, right? Let's just fill that in. What's that big sucker right there? Well, that's a QRS wave. This is a P wave, and that of course is a T wave. Notice that the T wave is further away from the QRS complex than the P wave is, and that's characteristic of a typical EKG. If a person had a heart rate of 78 beats per minute, what is the average duration of a single beat? Okay, and so what we have to do here is we have to do a little math. All right, so let's do that. And again, I would encourage you to write these calculations out because partial credit will be possible. So 78 beats in 1 minute. We got to get this to seconds, okay? So 1 minute is 60 seconds. Minutes cancel. You end up with 78 over 60 beats per second. But we don't want beats per second, we want seconds per beat. So what we have to do is flip this number upside down and you get 60 over 78 seconds per beat. And that, if you do the math, works out to 0.77. A person's duration for a single heartbeat average 0.85 seconds. What would their heart rate be in beats per minute? Okay, so 0.85 seconds per beat, okay, times 60 seconds in 1 minute, okay, and the seconds will cancel, so you'll get 0.85 minutes per beat, but we want the inverse of that. We want to flip that over, and if we do that, we end up with 70.6 BPM. So you just take 1 and divide it by 0.85 and you get 70.6. Okay? And that's how that math works out. That's called canceling units. It's a very important thing to learn how to do. Okay. The indicated interval of time in the above EKG is 935 milliseconds. Based on this interval, the length of a single heartbeat would be, and if we work that out, 935 milliseconds. Whoops, back up. Okay. Based on this interval, the individual's heart rate would be how many beats per minute? Okay, well, the length of a single heartbeat is 935 milliseconds. Okay, so we got to do this math here. One beat is 935 milliseconds. All right, we have a task here. What we want is beats per minute, right? So what do? Well, we find out how many milliseconds are in a second. Okay, so 1 second, one second down here has 1,000 milliseconds. Okay, so milliseconds will cancel, and then we got to go from seconds to minutes. So there's 60 seconds. That's a little hard to see in 1 minute. The minutes are going to stay around. Seconds are going to cancel. So bye-bye seconds. And so you end up with 1 times 1,000 times 60 over 935. beats per minute. If you push that through, you get 64.1. Okay? That's how to do the math. Okay. The interval from the beginning of the P wave to the QRS wave is called the what? And it's called the PR interval. The PR interval. The normal duration of this interval is how many seconds? And this is just something that you have to look up. And the range is anywhere from 0.12 to 0.2 seconds. 2 milliseconds, rather. Okay. Okay, next question. The interval from the beginning of the Q wave to the end of the T wave is called the what? And it's called the QT segment. The normal duration of this segment is how many milliseconds? And it's 0.43 normally. Okay. The interval from the end of the S wave to the beginning of the T is called the ST segment. The normal duration is 80 milliseconds. 80 milliseconds. Okay. This interval from the beginning of the Q wave to the end of the T wave is the QT segment. Okay. The normal duration of this segment is 0.42 seconds, or 420 milliseconds. Okay. So that's seconds, which is equal to 420 milliseconds. Okay. By the way, it was 80 milliseconds here for the ST segment, and it was 430 milliseconds here for the QT segment. Just want to make sure I said that right. I think I might have said 0.43 milliseconds earlier. This one, 120 to 200 milliseconds. Okay. Sorry about that. I just want to make sure you had the times right there. Okay. The duration of the indicated P wave, this is a P wave, is 104 milliseconds. Is the duration of this wave within the normal range? And the answer is no. Okay. Normal is between 60 and 100 milliseconds, and this indicates sinus tachycardia. Okay. Next question. The duration of the indicated QRS wave is 115 milliseconds. Is this duration within the normal range? And the answer is yes. The normal range is less than 120 milliseconds. Next question. The duration of the indicated T wave is 124 milliseconds. Is this duration within the normal range? And the answer is no. The normal range is 40 to 80 milliseconds. 40 to 80 milliseconds. Next question. The duration of the indicated PR interval is 160 milliseconds. Is this duration within the normal range? And the answer is yes. The normal range is between 120 and 200 milliseconds. Next question. The duration of the indicated QT segment is 360 milliseconds. Is this duration within the normal range? And the answer is yes. Normal is around 420 milliseconds. Next question. The duration of the indicated ST segment is 99 milliseconds. Is the duration of this segment within the normal range? The answer is yes. The normal range is between 80 to 120 milliseconds. Bottom line, you just have to know the ranges, and you can pull them out of your lab manual. You can also find them in your textbook. Okay, matching questions, which is which, and we'll just put them up here. Okay. P wave, the proper match is C. The QRS wave, G and B. The T wave, F. The prolonged PQ interval is A. The prolonged QT segment is D. And then elevated or depressed ST segment is E. Okay. Okay, now we want to compute some cardiac output, and remember your equations. Okay, you can't forget these equations. You have to be able to apply them. Your stroke volume is going to be your end diastolic volume. That's the maximum amount of blood the ventricles can hold, minus the end systolic volume, which is the amount of blood in the ventricles after they squeeze. Well, the cardiac output is equal to the stroke volume times the heart rate. Okay. So let's do some math. If the stroke volume is 75 and the end diastolic volume is 150, what is the end systolic volume? Okay, well, we got to write our equation down. Okay. SV equal EDV minus ESV. Plug in the numbers. 75 is equal to 150 minus ESV. And what that gives us, well, let's subtract 150 from both sides. Okay, and if we do that, we end up with 75 minus 150 is equal to 150 minus 150 minus ESV. 150 cancels. Negative 75 equals negative ESV. ESV equals 75. If cardiac output was 5.6 liters per minute and the heart rate was 75 beats per minute, what is the stroke volume in milliliters and liters per beat? Okay, so cardiac output is equal to what? It's equal to stroke volume times heart rate. Okay, so the cardiac output is 5.6. Okay, the heart rate was 75, and that's going to be multiplied by the stroke volume. So what we got to do is rearrange this. Stroke volume then would equal 5.6 divided by 75, and that gives us 74.6 milliliters per beat. And if we want to get that in terms of liters, we got to move the decimal point over 3 places, and that's going to be 0.0746. Okay? Good. There's an EKG. Here's an EKG recording, okay, pertaining to a patient. An EKG recording gives you the following information. ESV is 60 milliliters, end diastolic is 130, blood pressure is 120/80. Use all or part of this information to calculate the patient's cardiac output. Make sure the answer is in the appropriate units. Okay, so you just have to remember the formula for cardiac output, right? Cardiac output is what? CO equals heart rate times stroke volume. Okay, so CO is going to equal, now what do we have for heart rate? Okay, well, we got a 6-second interval here, and we got how many beats? 1, 2, 3, 4, 5, 6. So we're looking at 60 beats per minute, okay? So 60 beats per minute, heart rate. And then we got to multiply that by the stroke volume, okay? So the stroke volume is going to be equal to the EDV minus the ESV, okay? Well, the EDV's been given, right? 130 minus the ESV of 60, okay? And what that gives you for the stroke volume then is 70 ml. So the stroke volume, we can substitute that into this equation up here, 70 ml, okay? And what that gives us then for our cardiac output is 420 milliliters per minute, okay? And if we wanted that to be expressed in liters, that would be 0.42 liters per minute. Okay. Next question. What is the duration of a single heartbeat if a person is a sustained heart rate of 80 beats per minute? The answer is 750 milliseconds. Next question. Does an increase in end systolic volume increase or decrease cardiac output? An increase in end systolic means the heart's holding on to more blood after it squeezes, so that's going to decrease cardiac output. Does an increase in end diastolic increase or decrease cardiac output? So remember that stroke volume is EDV minus ESV, so if EDV gets bigger, then stroke volume is going to get bigger, so it's going to increase. And the last question, does an increase in stroke volume tend to increase or decrease cardiac output? Obviously, it increases it. Make sure to review your interactive physiology on cardiac cycle and cardiac output. I've got some very good videos that are already posted on Angel. Please watch those. Know the cardiac cycle and know how the conduction system works. Okay? Remember that video that we watched on the EKG and the conduction system and how the two events are related to each other. Okay? Alright, study this material. Obviously, it's going to be covered on the practical. If you have any questions, send me an email, and we will try and puzzle out any problems you might be having. Thank you very much, and I'll see you in class.